All right, let's talk about gears. You know, they're literally everywhere, from the car you drive to these giant wind turbines. They seem so simple, right? Just spinning objects doing a job. But behind that simplicity is this relentless, almost invisible quest for perfection. And that quest, well, it's driving a quiet revolution in how we make things. So let's dive in.
Yeah, it's a really good question, right? I mean, when something is this fundamental to, well, everything, where do you even find room for improvement? The answer isn't about reinventing the wheel, or in this case, the gear. It's about perfecting it in ways you can't even see. And that is the key. The future of this very physical, very real object is actually being built in the world of data, artificial intelligence, and engineering on a microscopic level. So today, we're going to go on a journey from the cutting edge of metal to the cutting edge of code. Okay, so we all get the basic idea of a gear, but creating a perfect one, that's a whole different ballgame. It's a challenge where the absolute tiniest, most microscopic flaw can have massive, massive consequences.
So here's why that perfection matters so much. These tiny flaws, they aren't just cosmetic. They create noise, vibration, and harshness. Engineers have a term for it, NVH. Think about it. That's the difference between a silent, smooth electric car and one that has an annoying whine. Those little imperfections also cause parts to wear out faster, that kill efficiency, and ultimately, they can lead to the catastrophic failure of some seriously expensive machinery.
So how do you actually achieve that kind of mind-boggling precision? Well, it all starts with the physical act of cutting metal. And here's something that might surprise you. These so-called traditional methods are actually a hotbed of really high-tech innovation.
You've got these workhorses of the industry, hobbing, grinding, and broaching. For decades, they've been the absolute backbone for making gears on a massive scale. But, and this is important, traditional definitely doesn't mean stagnant. Just look at a process like gear skiving.
Okay, let's zoom in on gear skiving for a second. Now this is super cool. What's so amazing about this method is how it combines the cutting and shaping all into one fluid, super high-speed process. It is insanely efficient and incredibly precise, especially when you're making those really complex internal gears. But of course, making it work is a huge engineering challenge. You have to perfectly calculate these incredibly complex, high-speed movements to make sure the cutting tool and the gear never ever collide. And at the same time, you're dealing with intense wear and tear on the tool and making sure the lubrication is just right. That's like a high-stakes mechanical ballet, where one tiny misstep means the whole performance is ruined. And the payoff for getting this right, it's huge. Just look at this stat from research by Kempchatna, Stefanova, and Klochko. By optimizing these cutting processes, you can slash your labor and material costs by a factor of 3 to 4. We're talking about massive, massive gains in efficiency.
All right, so we've got the overall shape down pat, but you know what? That's really only half the story. The next quest for perfection happens on a totally different scale, right on the surface, down at the microscopic level.
Just look at the difference here. On the left, you've got a pretty standard surface finish. See those tiny peaks and valleys? They cause friction, noise, and they make things wear out. But then you look to the right. That perfectly optimized surface, it's a complete game changer. It allows a thin film of oil to sit perfectly, which means quieter operation, a much longer life, and way better efficiency. So the big question is, how do you get that beautiful mirror-smooth surface? Well, one really slick new answer is a process called stream finishing. The best way to think about it is like a super-powered, high-tech pressure washer. But instead of water, it's using this really fine abrasive material. The result? As research shows, you get this incredibly smooth surface without any harsh chemicals, creating a perfect texture that holds on to lubricant and just dramatically cuts down on wear. Okay, now we're going to pivot. We've been talking a lot about the physical world, cutting and polishing metal, but the biggest revolution, the one that's really changing the game, is happening in the digital world. This is where data and AI are solving problems that are basically invisible to the human eye. And one of the biggest bad guys in this whole high-precision process is something totally invisible, something we're all familiar with: heat. See, when you're working at the scale of microns, that's millionths of a meter, even a tiny shift in temperature that you would never notice can cause a catastrophic error. So here's what happens. Picture a huge grinding machine. As it runs, the spindle gets hot, right? Simple enough. But that heat causes the entire massive steel frame of the machine to expand. Just a tiny, tiny bit. But at this scale, tiny is everything. That microscopic distortion is enough to throw off the whole process and make the final gear totally inaccurate. So what do? How on earth can you compensate for something like that? You can't just react to it by then the error is already baked in. The only way to solve it is to predict it before it ever happens.
And this is where things get truly brilliant. Researchers are now using advanced machine learning models, specifically something called a long short-term memory network, or LSTM. The simplest way to think about it is as an AI that has a memory. It learns how the machine behaves over time, so by watching the temperature, it can predict in real time exactly how the machine frame is about to change. Then it tells the machine to adjust for that error before it happens. It's literally correcting for a problem that doesn't exist yet. How cool is that?
And for our last stop, let's look over the horizon. Let's talk about a technology that could change all the rules: additive manufacturing. You probably know it better as 3D printing.
So this table kind of breaks down where we are right now. On one hand, you've got your traditional methods. They're still the undisputed champs for mass-producing incredibly strong gears. On the other hand, you have 3D printing, which gives you unbelievable design freedom. It's perfect for prototypes or really custom, low-volume parts. But as the research points out, it's not perfect yet. 3D printed metal gears can have issues with wear resistance, and tiny little problems in the process, like the metal powder getting degraded, can mess up the final accuracy. So the potential is absolutely massive, but we're still on the learning curve.
So after all that, what's the big takeaway? I think it's this. A modern gear is so much more than just a piece of metal. It's like a symphony where old-school craftsmanship, material science, and cutting-edge data science are all playing together in perfect harmony.
Just think about the journey we just took. We saw how even the oldest cutting techniques are constantly getting smarter. We saw surfaces being polished to near perfection. We saw AI literally predicting the future to cancel out invisible errors, and we even took a peek at what's coming next with 3D printing.
And that really brings us to the heart of it all. The quest for the perfect gear isn't just a mechanical process anymore. It's a computational one. It's a data problem. Every single rotation is calculated, every potential flaw is corrected in real time, and every surface is perfected to a level that was basically science fiction just a generation ago.
So I'll leave you with this to chew on. In a world where a piece of software is shaping a physical object in real time, where does the machine actually end and where does the data begin? It's a wild thought, and that line between the physical and the digital, it's getting blurrier every single day. Thanks for diving in with me on this explainer.